Hey, welcome back guys. This video is about solving constant acceleration word problems. And for this video, we actually had two of these warm-ups. So let's do the first one and then we'll do the second one. So before we begin, while cruising along a dark stretch of highway with a cruise control set at 25 meters per second, or approximately 55 miles per hour, you see at the fringes of your headlights that a bridge has been washed out. You apply the brakes and come to a stop in 4.0 seconds. Assume the clock starts the instant you hit the brakes. Calculate the acceleration of the car. Go ahead and pause the video. Okay, now there's going to be three ways that we can do this. I'm going to go ahead and just focus on two. The first one that I can do is I can go ahead and draw a graph of the situation and just throw in some numbers. It doesn't have to be precise, but I just have to basically put in some numbers to show me visually what's going on here. It doesn't have to be equally spaces. It's not to scale. It's just there to help you. So what I've got here is I've got a straight line, and it's a velocity time graph, and I know that the slope of this straight line is going to give me my acceleration. And I know that it's going to be negative because the slope is negative as well. And I went ahead and just put in a couple of interesting points here, 25 meters per second here, and 4, because I come to a complete stop here. So at velocity equals 0, there's a 4 there. Okay, from there, well, remember I've got my y equals mx plus b. Turning that into my mathematical model, I get the velocity is equal to at plus my initial velocity. And then from there, I can go ahead and throw in the numbers. So I've got the time of 4, and the velocity initially is 25 meters per second, and the rest is algebra. Okay, so I've got my meters per second there. I bring that term over, and then I've got my 4 seconds. I'm going to move that over, and so I find that my acceleration is negative 6.25 meters per second squared. Now let's compare this to the second method, all right? And that is just simply memorizing the equation. So we've got our acceleration is equal to delta v over delta t, and moving that out, we've got our v final minus v initial is equal to t final minus t initial. And my final velocity, because I'm at rest, is going to go to 0. And my initial time is going to be 0 because I'm starting the clock as soon as I start braking. From there, I've got my acceleration is equal to the negative of my initial velocity divided by the final time. Plugging in my numbers, chugging out the answer, I get the same exact answer of negative 6.25 meters per second squared. Negative. Now remember, just as a reminder for you guys, if you're in my class, remember if velocity is positive and your acceleration is negative, then you're slowing down. So the problem tells me that I'm slowing down, and I'm traveling in the positive direction, so my acceleration has to be negative. Okay, here's the second before we begin problem, and we've got a graph of velocity time, and I want you to determine how far the object traveled in the first 5 seconds of this graph. Well, remember that the area under this curve is what? Displacement, okay? So the area under that graph is displacement, so let's break it up into 2 easy chunks, okay? The first chunk from 0 to 3 seconds is the area of this box, so it's going to be 1.2 times 3, or 3.6. And then I'm going to go ahead and add to that the area from 3 to 5 seconds, which is 1/2 base times height. 1/2, or 1.2, times 2 divided by 2 gives me 1.2. Adding those two together, I get a complete displacement of 4.8 meters. Okay, today in this video, what we're going to do is we're going to solve word problems involving constant acceleration. Okay, so anytime we have motion with a constant acceleration, well, then we have these ugly equations that we're going to see here. And the first one is here. We've got our final velocity minus our initial velocity plus the acceleration times time. And that's going to help us when I don't have our change in position in the word problem there. The second one is going to be my change in position is equal to the initial velocity plus 1/2 at squared. And I'm going to use that one when I don't have a final velocity. The next one is going to be my v final squared is equal to my initial velocity squared plus 2 times a times delta x. And when I don't have time, that's when we're going to be using this one. And the fourth and final one here is I've got my delta x is equal to this bar over the v. Remember that? that's average velocity times time, is equal to my v initial plus v final divided by 2 times t, and this is valid only when I don't have acceleration. Now, you can memorize these, or sometimes your teacher gives it to you. In my class, in my AP class, I used to derive these things. It's ugly. You really don't want to see it, but I would refer to a textbook to see how these are derived there. For now, let's just use them in our problems, because that's the hard part right there. Just trying to figure out how to use them. So here's a problem here. We've got a bicyclist brakes from 21 meters per second to a stop in 32.3 meters. And we need to calculate the acceleration of the bicycle. All right, well, I'm going to show you a method here that I'd like for you to use for every single word problem. Not just in this class, but in any science class that you have a word problem in, you want to use this foolproof method. Okay, I've been teaching for quite a long time, and I've learned over the years that students can solve these problems much easier if they do the following. Okay, step number one. Okay, we're going to write down the known. Okay, we're going to list every variable that we know from reading the problem. Some of those variables aren't in numbers, so we have to look at the problem and decide, okay, if it comes to rest, then that means I've got a final velocity of 0. Or if it starts from rest, I've got an initial velocity of 0. Or later on, if it's dropped from a tower somewhere, then I know my acceleration is g, which is 9.8 meters per second squared. So you always want to write those down under k. Under unknown, or u, basically you're just going to list the variable that the question is asking you to solve for. The next step, I like to call it EQN, which is short for equation, and that's when you're going to write down the equation that you think might connect your known to the unknown, and then you're going to do the algebra, which is meaning you're going to isolate your unknown variable, and the last step, step number 5, just solve it by plugging and chugging out the answer with your calculator. All right, let's try this example. All right, so we've got our known here, and let's see. I see something here. This is from and to. These are two key words that I see a lot in word problems. Anytime you see the from and then to, that's going to tell you something. That's going to tell you that you have initial something, and then you have a final something. So I can say that my initial velocity is 21 meters per second, and then to a stop is going to be my final velocity of 0 meters per second. Okay, we also have my bike here, and from there I'm going to go ahead and say, well, okay, at the beginning of the problem here, it's going to go and move to here, over to the right. So let's take a look at both scenarios here, my initial and my final. So I can actually define more variables just by drawing a picture of it. So I can say, well, here at the beginning of my problem, I haven't moved anywhere. So I'm going to call that my initial displacement of 0 meters. And then later on, as time goes on, I've got my final position, which is 32.3 meters. Now this 0 here, this initial velocity, is not in the original problem. So it's one of those variables that you have to think about when you read the problem. Okay, so we have to read these problems carefully. Sometimes just by reading the problem, we can find variables that are hidden in the problem itself. Okay, the next step, I'm going to go ahead and write my unknown. Well, that's going to be my acceleration. And then the next step is my equation. All right, I'm going to look at them. There are 3 here. There should be a 4th one. But let's take a look at all of those. And I don't see, yes, there it is. Okay, let's try that one. Okay, so I've got my final velocity squared is equal to my initial velocity squared plus 2ax delta x. All right, let's go ahead and now do a checklist. What I'm going to do is I'm going to check every known here and compare it with my equation. And I'm going to put a check mark over here on my variable and a check mark over here in my equation just for bookkeeping purposes. Okay, so I've got my initial velocity here. Okay, check, I've got that. The next thing I'm going to do, I've got my final velocity. All right, I've got my final velocity here. Check, it's there in my equation. Now the next thing is, well, I have my initial and my final positions, but remember earlier we have our final minus our initial gives us our delta, or our change in position. So yes, check, we have that as well. The next step, I've got my unknown. Now when I write my unknown, I always want to write that variable equal to a question mark. Why? Because that will remind me that that's what I'm looking for, and if I go to the equation, there it is. I put a question mark over this variable to remind me this is the variable that I want to solve for. And if I look at the equation, I've got all of my variables known except one. This will tell you if you're on the right track. And so the rest is just algebra. So let's do our algebra. So I'm going to start with my equation here, and I've got my acceleration term here, and I've got another term here. Okay, it's a good rule of thumb to always keep the term you're trying to isolate on one side and move everything else. Not that you can't do it. I mean, you can do it, but you'd have to have an extra step by moving this term over here. So I've got two terms here. This term here doesn't have my acceleration, but this one does. So I'm going to move this one first. And it's added to my term here. So the inverse of adding or addition is going to be subtraction. So I'm going to subtract this term to both sides. It cancels here and ends up over here. Okay, and I'm still got my acceleration here. So I've got my 2 and my delta t. They're both multiplied by the acceleration. So the inverse of multiplication is division. So I'm going to divide both sides by 2 times delta t. And when I do that, these two terms cancel here, and they end up here on this side of the equation. So now, all I have to do is just put in the numbers and plug and chug and crank out the answer. Let's try another one here. So we got a car accelerates from 25 meters per second to 40 meters per second in 5 seconds. Assuming that the acceleration is constant, a key word, all right, that means if I've got a constant acceleration, so I can use those variables. I want to calculate the distance the car travels during this time. All right, my known, let's see, what are my knowns? I'm going to write my unknowns, and I'm going to write down the equation, and then from there, I'm going to do my algebra after I've done my checklist, and after I've done my algebra, I can plug and chug and get the answer. All right, so there's my unknowns, or there's my knowns. My initial and final is right here, hidden from initial to final. I've got my time, which is 5 seconds, and I've got my initial position at 0 meters. For the unknown, well, there's the question is asking, what is my final position? For my equation, all right, let's look at those again, and you can pause the video and see if you can guess which one it is by doing the little check marks like I showed you earlier in the last problem. But now I'm going to show you, well, it's this one down here. Okay, so let's go ahead and move that one up here. Oh, wait a minute. What'd I do? What's up? Okay, so here, look. I've got my change in position is equal to my average velocity times time, which is also equal to this here. But I don't need my average velocity times time. So I'm just going to go ahead and write this term and this term, and that's what I did here. Okay, moving on. Let's see, I've done all my checklists. Okay, from there, I know that my delta x is final minus initial. And well, it turns out that I didn't need my initial position because it was 0, so I got rid of it. All right, and then I plug and chug my values. I get 162.5 meters. All right, well, thanks for watching. And remember, if you need help or you'd like some tutoring, have a question, just go ahead and email me at monroe.watson@gmail.com.